So shall we start? The next talk is perspective talk by the Professor Arnab production of Indian Association for the Cultivation of Science and Other. He received his PhD in 2009 from Qatar Institute of Fundamental Research, and after he completed his PhD, he worked as a postdoc at Boston University and Max Planck Institute for the physics of complex systems. And since 2013, he has been a faculty member at the Indian Association for the Cultivation of Science, and now he's the associate professor at the institute. So today he is going to tell us about the emergent behavior of low and high energies in some prosperity. Please start.
Thanks. So I hope I'm audible to everyone. Yeah, I hope this mic is good. Okay, so firstly, I would like to thank the organizers for arranging this meeting and also inviting me to sort of give a perspective lecture here. I attended the last 1.5 days of the lectures and I really enjoyed it. I couldn't attend more because of some personal constraints, but anyway. So today I'll talk about emergent behavior because the theme of this workshop is emergent. At low and high energy, some frustrated magnets, but actually I'll just talk about one frustrated magnet and I'll talk about the low and high energy emergence in that. And you will also see in passing how various computational methods that has been discussed in this workshop are very relevant there. Because it's a problem which you cannot solve exactly, but nonetheless you can make rather interesting statements. Okay? Good. And of course, if you have any questions, feel free to stop me in the middle. It's okay if I don't finish my talk. Okay, so I'm actually not sure. Sorry, I'm actually not sure whether quantum spin ice was introduced in this workshop. Okay, good. So, right. So, so basically, I'll talk about this well-known frustrated magnet called quantum spin ice. Okay. And it's a spin-half model, exactly like the kind of problem Shubhra was talking about in the morning. And it's a spin-half model on a slightly complicated lattice. Okay, it's a lattice of corner-sharing tetrahedra. So it's some three-dimensional lattice of corner-sharing tetrahedra. And you could spin-half degrees of freedom there. What I'll show is, in this talk, what I'll show is that it has a stable quantum spin liquid phase in 3 dimension. This word stable is very important here. And you will actually also see the emergence of things called catalyst photons and emergent gauge invariants. And then you will say, why the hell am I talking about these? Because it's a spin problem which doesn't have gauge invariants. Okay? And depending on the time that I have, I'll also show that if I take related models, not a 3-dimensional model, but related models in lower dimension, it also has something which is sort of an emergence at high energies. Yesterday we heard that at high energies, the eigenstates typically have a volume law, but in these problems, you can have certain eigenstates which have area law, and these are called quantum any-body scars, and there's a very interesting order by disorder mechanism in the Hilbert space. Okay, that's the plan of the talk. Okay. But let's see how far we can go. So here is the model. So basically, there are effective spin-half degrees of freedom sitting on each side of the spiral flow lattice. Okay. So there are some spin-half. There's a spin-half degree of freedom here, 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 everywhere. And this is your spin Hamiltonian. Okay. So the spin Hamiltonian is like a two-spin object here, some SI, SJ, but it's an anisotropic Hamiltonian. It's not a Heisenberg Hamiltonian. It's what's called the XZ antiferromagnet. So this, of course, looks familiar. This is like the SX plus SY term. I've just written it in terms of spin half ladder operators. This term needs a bit of explanation. This is just your familiar SZ term, but this notation, SZ on a tetrahedron, just means the sum of the four SZs on a single tetrahedron. Then, of course, if you expand it out, the usual SZ operator plus some constant, okay? Because SZ can only be plus half or minus half. In particular, I would be interested in the limit where Jz is much larger than J perpendicular. And as I already told you, it's an antiferromagnet. So Jz and J perpendicular are both positive. Okay, so this sets the problem, very clearly the defined problem. Okay, so then you see, I sort of just point out two papers here. There is a vast literature, but I'm not sort of writing down everything here. So this is one of the first papers which sort of studied this problem and showed that there is a non-trivial spin liquid phase here. This was by Hermele, Fisher, and Balance. And I actually read this paper when I just started graduate school, so it had a deep effect on me. But so basically, in the title of the paper, you see the word photons, right? Even though this is a magnetic problem. And now this is a more recent paper in 2021, where you see the phrase fine structure constant. But this is again a problem of spins, right? So what the hell are these guys talking about? So what they are actually talking about is the low energy description of this problem. And as we anyway learned in the previous lecture, and also what you have been hearing instances of during this workshop, the low energy effective theory of a phase can look very different from the full microscopic Hamiltonian, and there might be various emergent symmetries, etc. So a word about materials, but I won't dwell too much in it. So these materials exist. They exist in labs, and people have done fantastic experiments in them. In fact, this is a slightly old review, not very recent, but you can have a look at some aspects there, some material aspects there. So basically, these are rare earth compounds which realize these spinized materials. And in these rare earth compounds, basically this A denotes a magnetic rare earth ion. Okay? And this B denotes some non-magnetic ion. And actually here, so this is again a problem where there is large spin-orbit coupling. Okay? And in fact, you should talk about, locally, you should talk about the quantum number J, not L or S. But if you again just look at the local structure and the effects of crystal fields, etc., then basically there's a low-lying doublet, and then everything else is at a much higher energy scale, and you can ignore that. So if you want to write an effective description in terms of spins, you can still have some S equal to half degrees of freedom. Third degree, S equal to degrees of freedom, and not S equal to half spins, if you want the net expressions. So that's a detail which I'll ignore in the rest of the talk. Okay? But it's a very important detail, because it ensures many times that certain terms which might not be allowed if it was just a spin half object are actually allowed due to symmetry reasons. Okay. Good. So now let's think about this problem. So this is my problem, and just to reiterate, this J. Good. So let's just think about the classical limit first. So let's put J per B equals 0. Right? This is already a non-trivial problem which has a long history. So one can, well, maybe not immediately, but almost immediately see that this problem has a massive ground state degeneracy. It's a very interesting static problem. So basically, the rule is that you go to each tetrahedron, and you need to put 2 spins down and 2 spins up, right? And then this SZ total on a tetrahedron would be 0. This is a sum of positive definite terms, so that's the minimum energy you can have, and that's your ground state. Of doing it, in fact, there's a macroscopically large number of ways of doing it, and basically, if you sort of do some hard labor and just construct one ground state, then you can ask, how do I go from this one ground state to another ground state, right? Now, you might naturally think, oh, I just take a spin and I just flip it, but that won't work. Because, of course, if you flip a spin on a tetrahedron, it would actually make this, sorry, I'm still getting used to this. Yeah, okay. It would actually make this thing non-zero, so it'll be an excited state with an excitation energy Jz, order Jz. But what you actually need to do is flip a bunch of spins such that you don't violate this constraint. And then, if you stare at this problem, you realize that there's a very interesting loop structure. So the structure is this. So suppose you go to a tetrahedron, there's some in arrow, and you choose some out arrow. Actually, there are 2 in arrows and 2 out arrows on each tetrahedron. You choose an in arrow and you choose an out arrow. So you know how to get in and you know how to get out, right? And you just do that, but you should come back to your starting. So basically, that just defines a loop. And if you just go in that loop, and then, so for example, this is the smallest closed loop possible here on this lattice, and then you just take these spins and you just change them to the reverse, right? So for example, this is like this, you just make this guy like that, the reverse of this, like that. So you basically just do SZ to minus SZ on this loop, then you will see that you are still in the ground state manifold. The simple reason is that you have taken a plus SZ equal to half and a SZ equal to minus half, and you have just sort of exchanged them, right? And that's it. Okay. And you have exchanged them in such a way in this closed loop that there are no endpoints. And of course, this is the smallest possible loop, and you can have bigger loops and still bigger loops. And this is, for example, a reasonably big loop, right? And just from this loop picture, it's obvious that this state has a macroscopic entropy. Because if you just start with small loops, you can draw a small loop here, a small loop there, small loop there, there, and you can just flip each loop independently. So obviously, there's a macroscopic entropy in this manifold. Right? Good. In fact, this was estimated by Pauling way back. This is the estimate. Okay, and so this is the thing at J per equals. Good. So let's go on. So as I said, even this problem is very interesting. So let me just dwell a bit into this, maybe 1 or 2 slides. That'll also be important in what I'm going to present next. So now suppose you're at a very low temperature and you have this macroscopic degeneracy of states, and you ask, what are the spin-spin correlation functions? That's one thing which people are interested in, both as a theorist as well as an experimentalist, right? So then, of course, the statement that there is a macroscopic degeneracy is not too helpful. I cannot simply calculate correlation functions from there, right? It's not very obvious how to do that. So then it turns out that you need to think in the right language. So the right language here is the following. So you should realize that there's a local constraint here. So the local constraint is that the sum of 4 spins on each tetrahedron is 0. Now you think about where you might have seen local constraints elsewhere in physics. Actually, not the first place, but one of the first places you encounter it is in electrodynamics. When you write divergence of E something, that's a local constraint, right? So you just try to write it like that. So basically, what you do is the following. So by the way, if you have any questions, please feel free to stop. So you just do the following. I'm sorry, these lattices are complicated, so it takes getting some used to. I still am not perfectly used to these lattices, but anyway. So right, cubic lattices are much better. But anyway, I could have done this on a cubic lattice also, but this thing is experimentally relevant. So yeah. Okay. So good. So now, you see, the trick here is that you mark the centers of these tetrahedrons, okay? And that sort of defines a dual lattice for you when you connect that. And that dual lattice has a name. That dual lattice is called the diamond lattice, okay? And if you Google up how a diamond lattice looks, you'll find it. Or if you are more hardworking, you should just draw the midpoints and just complete the lattice, right? So now, whenever you see a spin, which is so okay. Another property of the diamond lattice which is important is that the diamond lattice is a bipartite lattice. That's a very important. See, this was sort of obvious from here. You see, let's go back to this picture. You see, there are sort of two groups of tetrahedra, the blue guys and the red guys, if you wish, when you draw the entire lattice, and there's a clear distinction between them. So basically the centers of, the blue tetrahedra are like one sublattice of the diamond lattice, whereas the centers of the red tetrahedra are like the other sublattice of the diamond lattice. So you do that. Then suppose you are on the A sublattice or some chosen sublattice and your spin is up, then you basically draw a vector. So this is what I've tried to indicate in this figure. You basically draw a vector outward. Okay? Whereas if the spin is down, you basically draw a vector inward. That's your association. So you convert the problem of spins into a problem of vectors. Why did I do that? Because then this condition, starts looking like a more familiar condition. This is the lattice divergence of this vector. And I call this vector field magnetic field. But this is not a real magnetic field, it's just some effective description. Yeah. So, right, this looks like divergence of B. Now, you can convince yourself, so now it's an interesting counting exercise. Suppose you start from some state. I told you that you have to form small loops to go out of that state to another state, right? You can actually show that if you have small flippable loops, then these states contribute to a large entropy. Okay? And so, see, at very low temperatures in this problem, there's nothing but entropy. So you should sort of try to maximize entropy. Right? So basically, the principle is then you should build small loops. And so you should write an effective description at low temperature, which sort of favors small loops. Okay? And then you realize that small flippable loops give you a small average flux. The reason for that is simple to understand. Take the smallest possible loop. I have indicated the fluxes here. You see that this flux cancels this flux. This flux cancels this flux. This flux cancels this flux. But if you draw this long loop, like the red loop that I was trying to show you, you would see that this property is not true. At least if you post-grain a bit. So then the simple terms which are consistent with that is just a field theory like this, or an effective field theory like this. Right? But supplemented with this important constraint, the divergence of these events. Of course, I need to remember, right? Because of course, this term with a positive k favors small b, right? Because if the magnitude of b gets large at some point, then it penalizes. Now, this is a simple theory. This simple theory is just basically a Gaussian theory supplemented with this constraint. If it was just a Gaussian theory without this constraint, then I can calculate the BB correlators in momentum space, and they would just look like 1 by k times a delta function. These are the vector indices. You can think of it like x, y, z, the three components of this vector, right? But of course, you know, I have to think about this constraint as well. If I go to Fourier space, this is like q dot b of q equal to 0, right? So to sort of incorporate that, I need to kill the longitudinal components, and I just do that here. So I just kill the long. But you see, so this b is linearly related to the spin, apart from some phase factors. So the BB correlators are basically related to the spin-spin correlators apart from some form factors, right? Now you see this is interesting because if you look at this actually tells you that there is a singular behavior, right? If you take the q equal to 0 limit of this object, then it depends on which direction you're approaching from, right? So this is the so-called famous pinch points in momentum space for spin ice. Okay? So of course, in actual spin ice, there is a complicated pyrochlore lattice, and basically that's an FCC lattice with a tetrahedron at each FCC point. Then you have to choose some isometric directions, but you can do all that. And when you do all that and you do a full calculation, you get something. And in that something, you see that there are indeed these pinch points. And basically the reason for these pinch points is just this. Now you see there is already an emergent thing here. This K does not depend on Jz because you're in the ground state manifold, right? So it cannot depend on Jz. In fact, this K is a pure number. It just comes from entropic reasons, and you can almost calculate it. You cannot exactly calculate it, but anyway. So this K has an entropic origin. Okay? So right. Anyway, and then you can also calculate the spin-spin correlation in real space, and it looks like this. And this is actually a dipolar form in the sense that if you actually think of the spins as dipoles, and if you separate them apart, then basically this is how dipole-dipole interaction works. Right? So that's why it's called a dipolar. Okay, good. Is it okay? Any questions so far?
So this solution is without the constraint or with the constraint?
This solution is with the constraint because this term is because of this term. Without the constraint, you don't need this term. Any other question? Okay. So now you can think of the excitations of this classical problem, right? So the natural excitations are you flip a spin. When you flip a spin like this, then of course on this tetrahedron you don't have S total equal to 0, and on this tetrahedron you don't have S total. On one guy you have S total equal to whatever, maybe +2 in my units or something, and in the other guy it's plus or -2, right? But now comes an interesting thing. Suppose you try to heal this tetrahedron. That's very easy. You have to just flip one more spin, right? Then this tetrahedron would be healed. By healed, I mean it would recover S total equal to 0, right? But then when you try to do that, which I have done here, then all that you do is keep separating these charges, right? And if you just think about the classical problem, then of course, this configuration as well as this configuration as well as any other configuration are completely degenerate. But then when you take into account this entropy, this non-trivial entropy in this ice manifold, by which I simply mean, suppose you do a static calculation in which you pin the charge here and the anti-charge here. Sorry, the reason I'm calling it a charge and an anti-charge is now divergence of B is non-zero on this plaquette. And also non-zero on this plaquette. Similarly, divergence of B is non-zero here and non-zero here, but it's 0 here and it's 0 here. That's why by some abuse of language, I'm calling it as a charge and an anti-charge. Okay? So if you do a static problem, which is actually an interesting problem, where you place a charge here and an anti-charge here, and you just do the sort of, what should I call it? Yeah, you just do the partition function in this ground state manner versus you do it here. Then you will basically see that the number of microstates consistent with this guy and this guy are different from the number of microstates consistent with that guy, right? So that actually generates this effective Coulomb interaction between these. So basically, as I already told you, this K is emergent here. This K is emergent. You couldn't have guessed the K by staring at the microscopic Hamiltonian. In fact, the K does not depend on any parameters of the microscopic Hamiltonian. But how do you guess the K? A, you can look at the long distance spin-spin correlations. Then this prefactor tells you what K is. Or you can create excitations and separate them and look at their energy. Then, that prefactor tells you what the K is. Right? Good.
Arnab, I have a question regarding this interaction and its connection to and its connection to this number of microstates in the monopole sector as well as in the ice sector. So the fact that these monopole interactions can have either sign, can it also be traced to this counting?
Yeah, because sometimes you can reduce the number. Yeah,
on the same sublattice they have they are repulsive, and on the opposite sublattice they are attractive.
Yeah, it can be worked out.
Ice.
Right, it can be worked out. So that's kind of interesting. It can be worked out.
Okay, thanks.
Okay, good. Now we come to the full quantum problem. Now you see it's already interesting, right? So now you have this massively degenerate manifold of states, which satisfy the ice rule. So let's call them ice states. And now you turn on a small J perp. When you turn on a small J perp, then of course, there'll be fluctuations, quantum fluctuations induced, and this massive entropy would be quenched. Okay, so, but it'll be quenched in a very interesting way. Okay, so, we'll see how that happens. Good. So, now at least the first line of attack is obvious here. There are many ways of attacking this problem, but this is sort of slightly intuitive, so I'll go on with this. You see, there is an obvious way to attack this problem. So in the classical limit, the problem splits up into lots of manifolds of states. So the ground state manifold, which is the ice manifold, then something which has one monopole, one anti-monopole, right? Something which has two monopoles, two anti-monopoles, and so on. And all these things are separated by order JZ, right? The gap. Now you turn on a small J perp, and J perp is much smaller than JZ. So the natural thing you would do is a degenerate perturbation. And for understanding the very low energy properties, you would try to write an effective Hamiltonian in the ice manifold. And the standard technique of doing that is degenerate perturbation. Good. So you just do that. So in degenerate perturbation theory, of course, you can do lots of things. But roughly, if you want to imagine it, let's say this is your ice manifold and this is your whatever other stuff. Then you sort of do a quantum process. You go here. Then you do something, and then you come back. You can either come back to the same state as you started with, or you can come back to some other state. So this guy, I'm sorry, I'm really bad at this, but anyway, this guy is a diagonal process, whereas this guy is an off-diagonal process in your effective Hamilton. Right? So here, if you try to do that, you realize that the first non-trivial process, or the term, first non-trivial term that you can write down, which is not some constant, is an off-diagonal term, and that's this term at third order, and that's related to the fact that the smallest closed loop I can draw is like a hexagon. Okay. So what do I mean by that? So let's see. So what is the action of J perp? The action of J perp simply is if I have an up spin and a down spin, I just exchange these. That's the action of J perp. Okay. So I have drawn here. State consistent with the ice rules, right? So let's say I go here. Let's say I exchange these two guys. Then I know that this would violate the ice rules. So this cannot be it. Okay, then you say, okay, it doesn't matter to me. I exchange them twice. Then I'm back. It's like a diagonal term. You say I've generated a diagonal term. But if you count how many such diagonal terms can occur in each member of the ice manifold, you'll see that it's exactly the same. So it's like an identity. So the non-trivial term that you generate is actually this. You are on a hexagon, and suppose you can do the following. Suppose you can flip this guy. So you just exchange this white and black. You flip this guy, you again exchange white and black. You flip this guy, so you again exchange white and black. Now you just remember from the previous picture that the state is consistent with the ice rule, but it's a different ice state. So that's why it's an off-diagonal process. And it's a third order process in degenerate perturbation. So of course, the numerator would be J perp whole cube, and the denominator would be JZ squared, right? And you can work out the prefactor by the number of ways you can do it and stuff like that. Yeah. So you do that, and you land up into this. So this, to leading order, is the effective Hamiltonian of the low energy, right? For the quantum problem. This is a very interesting Hamiltonian. So this Hamiltonian acts entirely on the ice manifold, right? It doesn't take one state of the ice manifold to another state of the ice manifold. It acts entirely in the ice manifold. So it's an effective Hamiltonian written in this degenerate subspace. This effective Hamiltonian is actually a U1 lattice-based theory in disguise. Okay? There are again several ways of understanding it. I'll just try to take one way. Maybe it'll be more intuitive. Maybe it'll be less. I don't know. But anyway, the key point is this is a U1 lattice gauge theory in disguise. So you see, the microscopic Hamiltonian, which was the XXZ Hamiltonian, was not a lattice gauge theory. Really, it was not. It had just some global symmetries, right? In fact, the global symmetry was U1 cross Z, right? Because it was not like a fully rotationally integrated. But the effective Hamiltonian, this effective Hamiltonian has actually more symmetries. It's actually a human landscape. Now let me sort of raise an important thing here, which directly ties with the computational theme of this workshop. You see, this problem is again too difficult. Even though there is some simplification here is that this Hilbert space is larger than this Hilbert space, right? So that's a simplification if you want. But this is still a very non-trivial problem to solve. In fact, we don't know how to solve this problem. Okay? But this actually tells you something. See, the original problem, I could not have simulated it on my computer using, let's say, quantum mechanics. The reason is that the XXZ antiferromagnet on the pyrochlore lattice has something called the sign problem, okay, which I think was mentioned more than once in this workshop. Even though quantum Monte Carlo was probably not introduced, but I'll also not introduce it, but okay. Good. Now you can do the following. You can actually do a unitary transformation to change the sign of this J ring. So this J ring is this thing. Okay, so I'll just call the coefficient of this effective Hamiltonian J ring from now. And J ring is some term which is proportional to J per cube divided by JZ square. So basically, there's a unitary transformation which changes J ring to minus J ring. What is that? So basically, if you just look at this picture, and maybe if you just look at go to the black spins, you just do SZ to SCN, S plus minus to minus S plus minus. That's like a rotation in spin space for these black spins. Then you can automatically see that if you stick this unitary transformation here, then of course J ring goes to minus J ring. Good. Now, why is minus J ring nice and J ring is not nice? Because minus J ring does not have a sign. Okay. Now you trace it back to this guy. You see, J ring was odd in powers of J perp, which basically means I can switch the sign of J perp to minus J perp, and at least, of course, these two problems are distinct problems. They're separate problems. But at least in the limit, when J perp is very small, I should expect to recover similar things because of this property that J ring can be switched to minus J ring by unitary transformation. But now one is in business because this problem with the flip J perp can be accessed through quantum mechanics. In fact, a lot of progress in the field also came from quantum. Because as I said, you cannot solve this problem exactly. So of course, as a theorist, one can always wave one's hands, but if you cannot solve something properly, then of course you have to resort to all kinds of tools that you have at your disposal. Right? So good. So this is one nice feature which I wanted to mention. Yeah.
Yes. So essentially, you're solving the zero flux problem and trading it for the biflux problem.
That's
so then, but
even though I didn't want to go into that.
Yeah, put back the form factor for the actual physical spin correlations using this transformation.
Yeah, exactly.
And so, okay, so and then nothing happens to the photon sector.
No, nothing happens.
Yeah, because they don't carry that.
Yeah, exactly. That's the point. Nothing happens.
Okay. Thanks.
Right. That's good. Good. But that's kind of a neat property of this whole business, right? So at least there is a way to access the spin liquid using a sign-free Hamiltonian, right? Even though Hermele, Balance, and Fisher were originally looking at like 6 amp.
But can you sample the monopole sector also?
Yeah, in principle you can. That's more difficult. I don't know how efficiently you can sample it. I need to think about it a bit, but in principle you can. There's no sign problem.
Then the biflux would show up.
Correct. That's correct. Good. So there is another thing. So this problem, this Hamiltonian, can also be written in terms of a quantum dynamo model. Again, I apologize, I was not around for most of this workshop, so I don't know whether quantum dynamo models were introduced. But anyway, I won't also introduce them. But basically, the point is that these are some very paradigmatic models in condensed matter. So the idea is that if you go to the diamond lattice, wherever there are Sg equal to plus half spins, you put a dimer there on that corresponding bond on the dimer lattice. Then the rule would be, the ice rule would translate to the fact that there are two dimers at each, what is it called? At each, two dimers touching each side of the dimer. Okay, and then basically this term is like a ring exchange of these dimers, right? So the rule is that you can do anything as long as two dimers touch at each side of your dimer. Okay? So these problems have a very long history. Why do I mention this problem? I mentioned this problem because I'll consider the anomalous thermalization of such quantum dimer models in part 2 of this talk, if I ever reach part 2. Also, there is an important statement which one can make. One can deform this problem, which you cannot exactly solve, into a problem which you can exactly solve, and at least perturbatively show that this interesting quantum spin liquid should exist. So at least you, what should I say, breathe a sigh of relief as a theorist, right? So, okay. Good. So the problem is, see, this was the original problem written in some weird way, but it's not so weird in terms of timers. Basically, again, you have closed hexagons, and maybe I can draw there. Chalk. So in terms of timers, in this complicated lattice, diamond lattice, you can find hexagons, but these hexagons are not sort of on plane. They are sort of tilted in various ways. And so if you have a dimer configuration like this, you can take a dimer configuration with that. That's like the ring. Okay, good. So the original problem, I can go back to the slides now. The original problem was just a flipping, like a resonance of dimers like this, right? So again, it's off time in the timer basis. Now you add another term to it. So that's what I mean by deforming the problem. That's not the original problem. So this term is basically a counting term. So it just counts the number of these hexagons which are flippable. If a hexagon had, for example, two dimers, it couldn't have been flipped like this, right? So it just counts the number of hexagons which have exactly 3 dimers. So this Hamiltonian is called the Rorschach-Iverson model. This model has a very cool property, which is not terribly hard to see, but I'll just state the property. So I've chosen this coupling to be 1 by design, but there's a negative sign. If I choose lambda equal to 1, so basically if you make the magnitude of the diagonal and the off-diagonal term equal, then basically you know the exact ground state of this thing. And the exact ground state is just the sum of, so the quantum state is the sum of all possible dimer couples. So that's another instance of this loop picture that Shooter introduced in the first thing, right? Because again, you can think of these closed loops, and a dimer couple can be thought of as a loop. In fact, there are several loops, and so you just add them up, right? So that's so the wave function, the quantum wave function, is known at this point, R3 point. Now you can show perturbatively that if you move a bit inside, right, then this U1 phase is stable. I won't have the time to show that, but at least this part you can show cleanly. But you see, we are interested in this XXZ model, which is the limit when lambda is 0. That you cannot show perturbatively. So again, for that you needed numerics. And for example, these people, Shannon et al., they worked out the numerics for this quantum dimer model using a very interesting Green's function algorithm, and they could establish this phase diagram. Whereas Banerjee et al., they worked on the microscopic XXZ model, and they could establish that there is a quantum spin phase, right? Using one regard. Yes.
So now your phase diagram for the U1 quantum spin, like say here. So that is corresponding to the spin ice state.
Sorry, what is the correspondence to spin ice?
Yeah, that is the QS. What is the difference between the QSL and the spin ice states in your talk? So U1 QSL means
U1 QSL is not. See, spin ice is a classical problem. The ground state manifold is just this ice state or that ice state or that ice state. When you put in quantum mechanics, it's a very particular superposition of these states. right? That's the quantum ground state because the entropy is now going to 0, right? And then you build excitations of that. So this particular superposition brings the hell of a lot of difference. So in fact, I'll show that the spin-spin correlations, for example, of this phase are completely different to the spin-spin correlations of the spin ice, the classical spin ice problem. That's one way of thinking that the problems are different, right? But there are other ways. So, okay, the most important thing is that the classical spin ice problem had a macroscopic entropy. The quantum spin ice problem has 0 entropy. And so there's a rather interesting and a complicated superposition of states, which is your ground state. And then that ground state has very interesting properties. Excitations on top of that ground state has very interesting properties. Okay. Right, so here is the numerical evidence. So this is a later paper. I didn't show the original paper by Banerjee at all. This was a paper by Onoda and Kato, and this was a very nice QMC paper. So they could establish that really, as you keep lowering the temperature, there is this quantum spin ice phase which is formed. Now, there's already an interesting thing here. So we'll see that this quantum spin ice phase is a gapless phase. It's a gapless spin. Okay, but you see from quantum Monte Carlo, you see that there is a finite extent in parameter space where this phase is stable. So then you can obviously ask yourself what protects this gaplessness, because in this state it's not that you form an antiferromagnet or a ferromagnet, because anyway the original lattice was frustrated. So it's unlikely you would form such a state. So then, of course, you need to ask what protects this gaplessness. So anyway, so they also saw 2 broad peaks in specific feet as a function of temperature. So basically, those broad peaks indicated a crossover as you lower the temperature from a trivial paramagnet to the classical spin ice manifold, which is at a temperature scale which corresponds to order Jz. And then there is a lower, much lower temperature scale, which is J ring, below which you see this entropy of the ice manifold also quenching to 0. And that's why you get this second peak there, right? And so this is very similar to also the kind of double peaks which Massa was showing yesterday. I mean, at least at the surface, the reasoning is just that there are these 2 energy scales. But of course, that's a different spin liquid, this is a different spin. Okay, good. This is a slightly complicated slide, but sorry about that. Then the rest of the slides are easy. Okay. Okay. So now I want to sort of write, why am I doing this? Let me just tell you. I want to do some variable transformations into another theory which is not identical to this theory, but by the transformations that we do, we expect the same long distance properties. And that theory has the advantage that it looks like a more familiar translation. But yeah.
So Arnab, can I interrupt here? So the thing is that, so this is in the interest of the students. So you originally started with a spin model, correct? Right? Now to tackle that spin model, you figured out a kind of a magnetic field. Right? So which possibly is your gauge degrees of freedom or what you call it. And then that essentially brought in a constraint to the problem, and then you could solve it.
Yes, at very low temperature.
At very low temperatures,
yes.
right? So now at some point you made a comment that this spin problem could be mapped to a lattice gauge theory.
Yes,
right. So the question is that what is this lattice gauge theory? I mean, it's no. So why it is referred to as lattice gauge theory? Well, I don't come from that community, right? So
I see. Because you see, okay, so you can ask what are the transformations which keep a Hamiltonian invariant, right? So, for example, the normal transformations here would be, for example, you go to each spin. If you look at the full microscopic Hamiltonian, you go to each spin, you do a rotation by a theta, okay? And if it's the same theta, the Hamiltonian stays unchanged. Okay. Now, if you take this problem, this is very interesting. Now my symmetry generator is completely different. Let's say I sum these 4 spins on a generator. Okay. And I do the same rotation for this guy, about the z-axis. But it's a local rotation. I'm just doing it here. then you can show that this is a symmetry of this Hamilton. But I can do the symmetry operation independently here, here, here. Sorry, I'm much more used to a blackboard, so that's why I keep touching this, but I'm sorry. But anyway, you can understand, right? So, right. So this is a local symmetry. And one place where local symmetries arise like this are gauge theories, right? And from the transformation property, which I just told you, so the symmetry generator is basically exponential of I times alpha times the sum of these four spins, right? And alpha can be any number. From that fact, you can sort of realize that it's a U1 lattice. So this problem has more symmetry than okay, good. So now I do a lot of song and dance because, but anyway, I told you the main punchline, why this is a lattice gauge theory. Right? But I'll do this song and dance to sort of map it to a more familiar lattice gauge theory. Okay. But this is, you should keep in mind, this is not the same problem. This is a slightly different problem. But you see in condensed matter, we keep doing these transformations and we say that all those transformations are okay as long as they preserve long distance properties. It's in the same vein. But as a student, it's good to keep in mind that this problem is not exactly the same as the previous problem. Okay, so what are the transformations I do? First, I'll introduce, instead of spins, quantum rotors. So Arun already introduced quantum rotors to you guys, right? So for quantum rotors, basically the spin is replaced by a variable n, and n can be all possible integers, and the conjugate variable to that is phi, and phi, because n is an integer, phi is between 0 to 2 pi, right? Okay, phi is an angle, right? And phi and n are conjugate variables, so this is their combination. Okay. So the first step is, instead of spins, I place quantum rotors on the sides. The second step is that my lattice gauge theory is formulated, or the fluxes of the lattice gauge theory live on the dual lattice. Now, this is a very standard thing. I mean, for example, if you read Kogood's Reviews of Modern Physics, which is a very landmark reviews of modern physics. I mean, if you want to map a spin problem to a lattice gauge theory, usually you have to go to the dual lattice. Okay. But anyway, even in the classical spin-ice, you saw why I went to the. So again, you have to keep the fact that a sublattice is important. So, so maybe if this spin is up, right, you draw an arrow outward from A to B. If this spin is down, you draw an arrow inward, right, from B to A. Right? So basically, this arrow I now call an electric flux, right? Why is it an electric flux? You see, even though this is a scalar, this has a direction now, in the sense that r prime is obviously minus of er prime, right? So this is not a scalar. And this is your vector potential, so that gets mapped to this. And again, this plus minus comes from the sublattice stack. Okay. Actually, how much time do I have roughly? I have 5 minutes. Oh, 25. Okay, perfect. 25. So till 12:30. Okay. Okay, good. So you see, now there is a very important distinction. You should remember that the original microscopic problem had spin half degrees of freedom. That is why I put the shift here, nr prime minus half. You would see why this shift is important. Good. So you do these variable transformations. So these are the exact variable transformations, right? These are the variable transformations you do. So you just replace the spins by quantum rotors. This Arun already told you, right? Of course, the Hilbert space here is different from the original spins. Okay, but you still do it. Okay, and then you can write this problem like this on the dual diamond lattice. Now you see your original problem had spin half, so SG could be plus half or minus half. So that's why I put this fictitious U term here. This U term, if U is very large, enforces this problem. Right? So that's why I put this. And this other term was already present. in terms of these new variables of A, R, R prime, actually not A, R, R prime, let's first go to this step. In terms of these 5 variables, it becomes cos of phi 1 minus phi 2 plus phi 3 minus phi 4 plus phi 5 minus phi 6. But now, because there is this staggering here, if you write this term down, it becomes cos of A1 plus A2 plus A3 plus A4 plus A5 plus A6. That is nothing but a directed integral of this A field, which is nothing but the curl of it on the lattice. Okay? So now it starts looking familiar to a landscape, right? So, so this is your mu problem, right? So by this mapping of N to E and phi to A, I wrote this line. Okay, good. And to answer Indra's question again, this is of course the local gauge transformation you can do in this. This is more familiar, right? We learned it in textbook that this is a gauge transformation which we can do, and this keeps this in. Okay, good. So far so good. Any questions? Okay, good. But this lattice gauge theory is also kind of interesting because this E field is related to NRR prime minus half. You see, if this half was not there, then if you take the large U limit, then of course the solution is NRR prime goes to 0, which means that E goes to 0. But because of this half, even in the large U limit, basically there's a degeneracy here. NRR prime can be 0 or 1. And that basically costs the same amount of energy, right? So E can be plus half or minus half. And that's just a reflection of the original classical systems. Okay, so in gauge theory language, the large U limit is called the strong coupling limit. So in strong coupling, this theory is still frustrated, as I just said. So that's why it's called a frustrated gauge theory. So when you sort of work more in quantum spin like this, maybe you'll hear these terms, but that's all it means. Okay. Good. Right. So this formulation is actually very old. This formulation is actually very old. That's why I did it. Okay, because I wanted it to map to something. So if you read this paper, this is a very beautiful paper. If you read this paper by Kokut and Susskind, then you would see that basically they talked about how to write Vincent's lattice gauge theory in a Hamiltonian formulation. And they were basically dabbling with exactly these kinds of things, exactly these things. But there was a crucial difference. There was no half here, so this E was basically N. This E was not N minus half. But as I just told you, this makes a big difference. If E is basically N, then it's an unfrustrated gauge theory. Whereas if E is N minus half, I'm ignoring the staggering sign factors, then it's a frustrated lattice gauge. Right? So there's a difference. Okay, good. So now let's come to this problem, right? You see, now I wrote it in a particular language. So usually we call curl of A as B, right? But you see here the A is an angle, and that's why this thing comes in a cosine. I could not have directly written a B square term, right? Because a B square term is inconsistent with A being a periodic variable. Right? Okay. But I can write this term. This is, of course, consistent with A being a periodic variable. But suppose you are in a phase where this A field fluctuates very mildly, or the B field, rather, fluctuates very mildly, then, I mean, there is some sense in even trying to expand this thing, right? And if you do an expansion of this thing to leading order, you get curl of A whole square, which is B square. This is also something which we, for example, do in the XY model in 2 dimensions, right? I mean, the spin is, after all, angle there, but in one phase, you can ignore that it's an angle there and just think of it as a real field. In the other phase, the fact that it's an angle becomes very okay. So right. So, but you remember that this A is dual to E. So when A fluctuates a lot, E does not fluctuate so much, whereas when E fluctuates a lot, A does not fluctuate, right? Because it's like, yeah, it's just from this, right? So good. So now you see, if you just write the standard gauge theory, which was this unfrustrated gauge theory, then if you are in the small u limit, so what do I mean by, so in the small u limit, you see this E term can fluctuate a lot, right? Because it doesn't cost too much energy to change E to E plus 1 or E minus 1, right? So E fluctuates a lot, but because E fluctuates a lot, A does not fluctuate so much. So you can expand cos of curl of A to D square. I'm giving a very heuristic picture here, but you can of course do these things much more properly. But I hope you see what I'm trying to say, right? Whereas in the other limit, when U is large, you cannot do this thing, right? You cannot do this expansion. Then the fact that this A is a compact field is very important. Then it's very important. So, by the way, this is also called compact U1 gauge theory. The reason it's called compact is because this is an angle. Okay, good. So here it's roughly easy to understand what's happening. When U is small, then this theory is deconfined just from the logic I told you. Whereas when U is large, you expect it to be confined. Okay. When it's deconfined, it's like your usual electromagnetism, which we are very familiar with. Okay. Then you'll have a photon phase in 3 dimensions, and the charges will interact by a 1/r potential and so on. Okay. When it's confined, it's very different. Okay. In fact, the magnetic monopoles condense. So if you look at the correlation functions of this magnetic monopoles, they are non-zero here at long distances, but they are zero here at long distances. Okay. Okay. Good. Anyway, now in this frustrated lattice gauge theory, this large U limit is not obvious. It's not obvious whether this theory is confined or deconfined. In fact, all the numerics suggest that this theory is deconfined. But this is already a non-trivial statement. You needed a reasonable amount of numerics to even suggest this possibility. Of course, theoretically, there are certain reasons to believe that, but I mean, there is no way you can argue that it's deconfined all the way. Okay. Good. So now, I said several things. I did not justify most of them, but if you believe all that, then what's the consequence? Okay. The consequence is the following. The consequence is that this microscopic problem at very low energies maps to this problem, where I can think of E and B as some real variables, some non-compact variables, vector fields, of course, and this is the 3+1 dimensional quantum electromagnetism. And again, just like K was emergent there, you remember there was a K which came out of entropic reasons. These K sub E and K sub B are also emergent properties. There's a lot of coarse graining or renormalization that you need to do for these things to emerge, right? But again, as in the previous problem of classical spinize, if you measure appropriate spin-spin correlators or appropriate quantities, you can get a handle of these things. And these things are important. For example, the speed of light is basically square root of Ke divided by Kb. Okay, so of course it's important. Okay, good. So from this argument, what is the sort of low energy spectrum that I would imagine? So now you see what has happened is there was this classical ice manifold. It has split due to your quantum fluctuations, right? Now basically let's say the ground state is at 0 energy, and I am now interested in the excitations. So one class of excitations there are linear modes. So the dispersion goes like this. Here. The dispersion goes like this, right? So it's a linearly dispersing mode. And the reason I call it a photon mode is because unlike a magnon, which has 3 polarizations, this mode would only have 2 polarizations. Okay. Good. That's one property. Okay. So now there are other modes. You remember there was I already told you how the spin-on anti-spin-on looked in a picture. That scale is at sort of JZ, right? And of course, quantum fluctuations induce some dispersion. So it's not a flat thing. It's like something like this. So let me call them electric monopoles now. And there are some more complicated objects at lower energy scale which are magnetic. Now, one immediate consequence of this thing, if this thing is true, then the electric monopoles now have an energetic Coulomb interaction. See, earlier the interaction was just some entropic interaction. Okay, I mean, so if you are at finite temperature, basically the interaction would be proportional to T. But now if you are at very low temperature, you actually get an energetic interaction there. And that energetic interaction is again dictated by this term K sub, this effective fact. Similarly, between the magnetic monopoles, you again have a 1 by R Coulomb interaction with the prefactor dictated by this. Good. Now, for example, let me ask a basic question. How can I extract the speed of the artificial photon, right? Because I'm saying there's a photon, what's the, let's say, the numerical verification? The verification is, if you go back to Onoda-san's paper, and if you look at the energy, you see that at very low temperatures, the energy seems to go as temperature raised to the power 4, which means specifically it goes as T cube. But in this phase, numerically, they could find no long range order. But whenever this thing goes as T cube, if you remember the previous talk, basically that's suggesting linearly dispersing modes in 3 dimensions, and that's exactly what it is. And you can fit the extremely low temperature data here to a T to the power 4, the energy, that's this dotted line, and you can extract the speed of light. So this speed of light is an emergent point. So this already told me that the square root of Ke by Kb is this number. Okay, good. So far, so good. So you see, all I'm trying to say is that I could not have a priori guessed these numbers from my microscopic sample. Of course, everything is present in the microscopic sample. Okay, good. So now let me try to do this. Now you can even calculate the Now you can again calculate the correlation functions here, the electric field, electric correlation functions here. Here you will see that the answer is different, even though divergence of E is 0, because you're in the ice manifold. So of course you'll have a term like this, because you remember the logic of this, to kill the longitudinal component. So you'll have a term like this in momentum space. But you see, in this classical spin ice, you just got this factor. Here you'll get something else. Why do you get something else? You see, at very low temperature, I'm saying this thing is like Gaussian electrodynamics. So Gaussian electrodynamics can be reduced to a bunch of harmonic oscillators. Maybe all of you have done this exercise when you do black body radiation and stuff like that. So because these are harmonic oscillators, then you can use virial theorem to calculate the expectation value of this guy, right? You can think of this guy as the kinetic energy and the other part, Kb times B square is the potential energy. So this expectation value is just half of the 0-point energy, right, of the quantum oscillator. Or the 0-point energy is just related to omega, right? And omega is, of course, related to the speed of light. So therefore, to make this thing consistent with that, you need to just stick it in this, right? So there's a big difference between this correlation function and this correlation function, because this is finite at the pinch point, this prefactor, whereas this is 0. So then if you Fourier transform it in real space, you get a different function. Okay. So, but one minute. But if you heat up the, let's say heat up. If you heat up the quantum spin ice like Onoda et al. Were doing, you would actually go smoothly from this guy. You should, at long.
So basically, the quantum thing is different from the classical, because in the quantum you are starting from the 4D dipole correlations and making it equal time.
Yeah, that's one. That's another way of saying it. I just did this because I just did it because this may be a shortcut.
Okay.
But yeah, essentially the thing is, because there's also imaginary time there, it's a 4D theory. Good. Now you can ask me, is it enough in QMC to see linearly dispersing modes? Well, I would say this is already promising, but to me, it's not a smoking gun thing. So there is room for much more work. especially on how to write clever Monte Carlo algorithms. As people who do these things, they very well know that itself requires a huge amount of creativity, right? So, so what do I mean by smoking gun proof that there is quantum electrodynamics at lower energies? Smoking gun proof is this. So I just told you how to look at the electric field, which of course in the original variables is related to the spin-spin correlation. But you see, there's another correlation function here, which is the magnetic field. Now that is a bit difficult to extract. But if you go back to the dictionary, which I sort of told you about, anyway, I'll give this slides to the organizers if the dictionary is forgotten. But anyway, if you go back to that dictionary, this ring exchange term basically looks like cosine of t. So at least to leading order, you can extract the b square correlation. Right? But you see, it's a bit more complicated than the electric field. But somehow, if we do something clever, so that we can somehow extract the magnetic field correlation function, then electromagnetic duality of quantum QED tells us a very powerful statement. That at long distances, the spin-spin correlation functions multiplied by this prefactor, this emergent prefactor, should be exactly equal to the magnetic field correlations multiplied by that other prefactor. This is a very non-trivial statement, right? So if people can approximately show that, that'll be very cool. Because this is a spin-spin correlation, whereas this is some very higher order correlation, right? So there's no a priori reason that these two correlation functions should be identical up to a rescaling factor. In fact, the rescaling factor is c squared, right? Speed of light square, and you know what is the speed of light. So there are various checks here. This is a very non-trivial. But the problem here is, just because a quantum Monte Carlo has no sign problem does not mean it's trivial to do it. Okay, okay, it just means that you can hope to do it, but there is a big difference between writing an efficient algorithm and an inefficient algorithm. And the problem is, people have done very clever things here to write semi-efficient algorithms. Oh, sorry, I forgot to mention a reference for this. So there's this reference by Anders Sandbeck on computational methods, which you can easily find on the archive. That's a very good place to read about QMC as well as exact diagonalization. So I'm sorry, I forgot to write the archive numbers for that. But anyway, so the point is that in this problem, as well as many other problems of strong correlation, people don't really know of the most efficient ways to sort of implement detail balance in a clever, in an efficient way. Anyway, so I just wanted to highlight that because it's a workshop on computation. Okay, now my time is really limited in the next 5 minutes. I'll just add the punchline of the rest of the story and then I'll stop. I won't go to the details. But sorry, I'm rushing through this. There's a topological degeneracy of this quantum spin liquid state as well. And in fact, if you take a charge and an anti-charge in a torus, I showed a picture to you guys already, and just wrap them around in a periodic boundary condition so that they annihilate. That sort of puts a non-zero winding or flux in the torus. Okay, and using this idea cleverly, actually, I think I showed this paper originally. This 2021 PRL did some ED calculations, and they could actually estimate the fine structure constant, which is a dimensionless number in three-dimensional QED for this guy. This fine structure constant turns out to be 0.1 when they look at electric molecules. But 0.1 is very different from 1 by 137. But of course, that's okay. Well, that of course shows that matter is strongly coupled to photons here, for one. And for the other, it shows that this is not really similar to normal QED, even though the photon mode survives. But that's okay. Yeah.
So which matter are you talking about? The magnetic matter or the electric matter?
Electric matter, which is local in SC. The electric monopole, which you can create by a spin.
Yeah. So why is that the relevant fine structure constant to calculate? Because that's the highest energy.
I know. That's not very relevant. I just quoted this number because at least it shows it's different from standard. Yeah. But to me, that's not the most relevant.
Yeah. Is there a way to calculate coupling constant to the magnetic
That's
sector?
more different. Yeah. I don't know of an obvious thing to do there, but it's a very interesting. I don't know how to do it efficiently.
Nice.
Yeah, but I agree. It's not the. But it's still interesting because this number is already so large. But I agree.
Yeah, but if this number is large, then the other number might be smaller.
Exactly. That's
Uh,
why duality.
Yeah.
That's even though I don't know the duality for the fine structure constants. Yeah. Exactly. So. Okay, so in the next 3 or 4 minutes, I'll just tell you the punchline and then. Okay. So you see, I was also talking of emergence of emergence at high energy states, and I in particular said that in these class of problems, you can actually construct high energy states which have very low entropy. So they look like ground states, even though they're sitting at very high energies. Okay? So that actually has a big ramification on thermalization properties of these kinds of things. Okay? So what that means is that, see, so maybe again, many of you are familiar with these things because for the last decade or so, many people have done very interesting things here. So suppose you just take a simple product state, right? And you just evolve it purely unitarily, right? So this is just quantum mechanics. Then, if you look at local correlation functions for a sufficiently complicated system, you realize that if you wait in time, you can actually recover thermal answers. Of course, this is paradoxical because unitary evolution cannot erase any quantum information. But the point is that as you do this unitary evolution, your quantum entanglement moves in a non-trivial way, such that this memory of the initial state is pushed in time to higher and higher non-local operators. And therefore, if you have a local probe, you cannot extract that information. But that is basically saying that you have lost almost all the memory of the initial state. But that basically means that you have thermalized, because think about it, when you do StatMech, that's exactly the chain of logic. Right? Okay. So good. So then there is a way of formalizing it. There's something called the eigenstate thermalization hypothesis, which states that many body eigenstates of local Hamiltonians, which have a finite energy density. So note, I'm not at low energy, I'm at high energy, because I say finite energy density. Right? For such many body eigenstates, if you compute local correlation functions, they appear thermal, and the temperature is just set by this local energy. So here, what is actually happening is, remember the xxz point was the lambda equal to 0 point of the quantum diamond model. So at lambda equal to 0, at that xxz point, there is an index theorem. There is a very interesting index theorem. So I'll just tell you roughly what's happening in maybe 5 minutes, and if that's okay, and then I'll stop. Right. So basically, at lambda equal to 0, which is the xxz problem, there is an index theorem. I'll tell you the conditions that you need for that, which says, well, basically you get two things. First, that your spectrum at lambda equal to 0 is symmetric in E and minus. For every state in with an energy eigenvalue E, and I'm talking of many body eigenstates, right? It's an interacting problem. So for every state in E, you can find a corresponding state with exactly negative of that. So that's why 0 has a special meaning, right? But what you can show, if certain conditions are met, then there is actually a macroscopic number of exact 0 modes. So the number of the 0 modes scales exponentially in the number of cases. Okay, that normally does not happen so frequently, but the conditions that you need for that are rather weak. So in fact, many problems have that. Then, if you add some extra non-commuting terms to your Hamiltonian, one example was that Rorschach-Stevenson term I put, that lambda term. That's a non-commuting term. But that non-commuting term would break this index theorem. Then, of course, you would expect that the 0 modes hybridize with the non-zero modes, right? But what you can show, and I think this is a generic feature, what you can show is that even though most of the 0 modes hybridize with the non-zero modes, there are some 0 modes which survive. And these 0 modes have anomalously low entanglement entropy, and you can see their ramification in the sense that There is a class of simple initial states, and these zero modes have a big overlap with these simple initial states, and they don't. So I'll be very quick now. So let me just give you an evidence of that. I'll skip many details. So here is a numerical evidence of that from exact diagonalization. Okay. On a ladder system for the quantum wave. Of course, I cannot do ET in full 3 dimensions, but I have no reason to disbelieve that this won't happen in 3 dimensions. There's nothing in particular in 1D. Okay. So basically, there are 3 states I take. 3 initial product states. These initial product states have exactly the same energy, but I have chosen them such that they are local correlation functions, some electric field correlation. They are very dissimilar at 0 time. I can, of course, engineer such initial states. So you see, this is the hallmark of thermalization. I just let it evolve unitarily. You see, this local correlation function just becomes identical at late time. This is the hallmark of thermalization. But this initial state actually has a large overlap with this anomalous 0 mode, and therefore it does not thermalize. Okay. Good. So, sorry, I'll skip many details. You can see the signatures of that in, for example, the bipartite entanglement, right? So most of the states have a very high bipartite entanglement entropy, which is consistent with volume law, which you discussed in these lectures. But these stars or these anomalous zeros have a much lower bipartite. In fact, if you slightly deform the system to another model called the quantum dynamo model, okay. So the only change in the quantum dynamo model is you have the same dynamics of fluxes, but now basically the rule is that you don't have 2 in 2 out, but on one sublattice you have 3 in 1 out, and on the other sublattice you have 3 out 1 in. So that's it. So if you do that, and in particular if you take periodic boundary conditions in both directions, and if you fix the width to 4, but let's say the length is arbitrary, so it's like a thin torus with a fixed width, then you can write a class of exact high energy states, which can be written in some tensor product form. But these are high energy states. Okay? And these tensor products are interesting. So these Legos, if you wish, this is really a Lego game. These Legos have an internal structure which is highly entangled. At their boundaries, they have some rules. And these Legos are more than one kind, just like our Lego boxes. And only if you satisfy some rules can you stick 2 Legos together. Okay? So this is really a Lego game. You play this Lego game and you can construct an exponential number of Lego scars for this thin torus problem. I'll just show you some pictures and stop. For example, for example, this is one Lego. There are some emergent singlets. So the singlets are formed of a clockwise and an anti-clockwise placket. And then there are some more complicated objects. I don't know what to call them because there are some bunch of singlets here, but there are some objects which are composed of 4 entities, and you can keep playing this game and it becomes more and more entangled. And yeah, so basically I hope I have illustrated that in this one example, but on different lattices, there is emergence both at very low energies and at high energies, right? So yeah, so as we all know, frustrated magnets are a fun thing to study, and I hope I've just reiterated that. So thank you.
Very much for the So the topic is now open for the questions. Do you have any questions, comments? So I have one question about the emergent parameter K. So you said that it is coming from the entropy effect.
Oh, emergent what?
Emergent parameters, energy
Oh, yeah,
K.
okay, in the classical profile.
In the classical, you said that it's coming from the entropy.
Yeah.
So it means neither is that it's independent of the original interaction J.
Exactly.
How about in the case of quantum model? So
Oh, in the quantum model, it's a subleading correction which is unimportant at low temperature. Because there's already an energetic term plus this term, but this term is proportional to temperature because it's an entropic term. So if you go to very low temperature, it's subatomic.
okay. So yeah, my question is the KE and KB.
They are energetic. They are,
Okay.
Yeah.
I see.
they come due to the fact that your quantum wave function has a complicated superposition, and then when you create excitations on top of it, you actually cost energy, and yeah, you can go below. Those are energetic.
Okay.
They are not energy.
Thank you very much. So,
I also have a question about the pinch point filter.
The what?
A pinch point
Oh, yeah.
filter in the crystal state and the quantum state. So there are the difference in the shape in the.
Yeah, so the key difference is the following. If you go to momentum space, there isn't a very big difference. But, and I think this was already observed in these quantum molecules. Even though I cannot remember which difference first observed. Sorry. Oh, yeah, yeah.
Yeah.
So you see, suppose you do what Onoda-san did. So you cool the system down. What you will see is when you go to temperatures reasonably below Jz, then you will start seeing these pinch points. But this, if you wish, the amplitude of this pinch point would then start crashing down as you cross the other temperature scale Jz. So this would happen in ADFX. And then you just go to 0. Right, so that's the distinction. Here it's 1 by k, whereas here it's proportional. This factor is this.
So the quantum spin ice state can have the zero weight at the
Pitch point. Exactly. That's the point. It has 0 weight. Exactly. So when you heat it up, weight starts appearing.
Okay, I see.
Yeah. And then when you further heat it up, then this factor goes. Then it becomes a trivial parameter. So that's this hierarchy.
I see. Okay, thank you very much.
yeah. Any other question? Online? So do you have any questions in online participants?
Hello, sir. I have a question. May I ask that? Hello. Am I audible?
Maybe that person can chat, put that question in chat, or I can answer.
Yeah.
Oh, Jubilee wished.
Already fine. Please, but
We cannot hear you. Can you please type in your question in the chat box?
Oh, I mean, am I not audible?
You wished.
Yeah.
We cannot hear you.
No.
Please type your question in the chat box.
Okay. Yes,
Now we don't know what to do. So we are frustrated.
Right. You post your question in the chat box.
Oh, maybe he or she can ask me the question over email and I'll answer.
Flux.
Oh, I see. Yeah, okay. The responsible loops give low average flux. Yes, that's correct.
When you take the
What is the question? Can you please choose? Okay. Oh,
don't, you do not get it. Get it. So my question is.
Oh, I see. So maybe okay. I hope that's the question. So I'll just illustrate that very quickly. How do I go back? Okay.
The smaller loop.
I'll just illustrate it very quickly.
Depends.
Let's go back to this picture. So I hope Jyoti, it's clear to you that if I'm here on a small loop, on this hexagon, why the average field goes to 0. If I just coarse grain this much, right? I have to coarse grain by an amount, by spatial extent. So I need to tell you that, right? But now let's look at the long loop, this guy. So this long loop in red, of course, encloses a much bigger sort of perimeter. Now if I do the same coarse grain, I don't know whether she can see my pointer. But if I do the same pose range, similar in spatial extent, then of course these four fluxes point in the same way. They don't average to zero. So that's what I had. Yeah, that's correct. So entropically, it's favorable to use the smaller loop, and because it's entropically favorable to use the smaller loop, that's why the low energy field theory looks exactly like this with a positive K. That's the answer. I hope that's okay. Okay.
Good. Thank you very much. So, Arnab, so let's start the computer again.
Okay, so we break for lunch, right? And we again meet 2 o'clock.
Okay.
You have to thank the chair.
After the session will start 3 o'clock.
So let's thank the chairman for
Thank you.